So hello everyone. My name is Asmae Moutaoikil. I'm a PhD student at University of Bordeaux, and I'm working on the experimental and numerical methods to characterize adaptive facades. I'm under the supervision of Laurent Morat from A2M, Institute of Mechanics and Engineering, Tatiana from l'Asie, La Rochelle, Tintin Voktou and Thomas Rest from A2M. So I'm going to start with presenting the context, motivation, and what is the research question that we are trying to resolve, the proposed methodology, and an application of this methodology for a case of study, and finally, results and perspectives. So as you all know, the facade is an important element of the building. It is an interface between the indoor and outdoor environment, and it's responsible for the exchange of heat, airflow, daylight, and acoustic. So, for instance, if we take the example passive facade, where normally an average value of a KPI can be considered sufficient, even though you just talk about the variability of height. The passive facade actually cannot adapt to climate in a positive way, means that we could have in winter heat loss and in summer have heat gain, which in turn can impact the heating and cooling load energy consumption, and also the occupant's comfort. So to conclude here, a passive facade cannot optimize for both winter insulation and summer shading simultaneously. Therefore, there is a need for adaptability. So one concept that can be a potential solution for such a case is the adaptive facade concept. So adaptive facade is defined as a facade where the properties are dynamic and it can adapt to the climate variations. And also we could have control operations that are involved. And those two pictures represent some examples of adaptive facades. You have here a green facade where normally you have the evapotranspiration phenomena that can lead to have a dynamic heat flow. And here you have movable shading where the solar gain is adjustable smoothly. So what is the problem with this adaptive facade? It's actually I'm focused more on the thermal level. The thing is, if you want to characterize a passive facade, you can consider that the KPI, like the U value, G value, one value can be sufficient, one single value can be sufficient. But the thing with the adaptive facade is that you have multiple states. You have dynamic states, and you cannot consider that one value can characterize the behavior of such a facade. And in the same time, you could have like an instant idea is to model each state. But the problem is, if you model each state of your adaptive facade, you ignore the transient states and you ignore the accumulative effects of the states. I can give example quickly, like if you have a shading device, a Venetian blanks with a glazing, and the Venetian blanks operate in like different slat angles, you cannot characterize the system in the whole day with one G value of 6%. So the question here is how actually we can evaluate the thermal performance of such a system, especially under climate conditions, because practically the facade will be installed outside, so we want to work with an outdoor effectiveness. And also during early stage design, because when is important to do this certain characterization is in the early stage design where you want to know what is the optimal design of your adaptive facade, what is the optimal control operations that you're going to use. So it's actually where this problematic needs to be resolved. So for the proposed methodology in my PhD, it is a two-step characterization hybrid approach. So basically, you want to characterize your adaptive facade, means that you want to estimate a KPI, an indicator of performance. So in order to be able to isolate the the phenomena that this adaptive facade, the heat path that this adaptive facade modulates, you need to master well the behavior of the test cell around that. So for this, you will need an early step, which means to characterize a passive facade to calibrate your outdoor test cell. And at the same time, this can bring you a comparing benchmark with the performance of your adaptive facade. And so here you collect measurements of temperature fluctuations inside your test cell. This is an effect. And of course, you need to arrive to the KPI, which is the cause, the parameter. And in order to link between the two, you need a model to be able to calculate it. So a case of study of this methodology will there is other detailed steps of this methodology, but in order to apply it, we worked with the shading device that is diagonal. The slats are diagonal and they are not movable, but the tilt angle of this slat was calculated by a third-party company, where this shading was designed to allow solar rays during winter and block them during summer. And also it have an azimuthal preference if you install it. Toward the south, it allows more the rays in southeast and block them in southwest. So the test cell is oriented to the south, and the reference facade that we had, it was a double glazed. And this was in the experimental aspect. For the numerical aspect, we worked with RC model, resistance capacitance model. And so yeah, the KPI that we were trying to reach is the direct transmittance of the whole system, meaning the shading plus the double glazing. And so we need to know how accurate is the identified KPI by the model. In order to do so, the validation was using Radiance software, the ray tracing technique. We calculated with Radiance the direct transmittance. So quickly, in Radiance, you have here, this is the fenestration system, and this is the incident hemisphere, and this is the reflective hemisphere. So you send rays here numerically, and then you can calculate probably here the technique is VSDF, the directional scattering distributed function, where you can have the distribution of your transmittance on each patch. And it's in function of incidence angle and also local azimuth. So here the numerical model, this is a realistic picture of the shading. You can see it's in the outdoor, so it's in the exterior in front of the double glazing. This is the meteorological station. And you can see here it's oriented to the south. And when the rays are aligned with the slats, you have a maximum transmittance. But once the slats, the rays are not aligned, which means here you have southeast, you have southwest, they are blocked. So here for the RC model, I've modeled the multiple heat pathways. You have convection or induction through the system. So we have a simplified model where the part that interested us, it is this total direct shading RC in function of time, and it's the unknown parameter that we are trying to estimate by this model, by this RC model, and the solar gain is applied to the envelope temperature. The envelope is heated. So for the results, here in orange, we have the direct transmittance estimated by the model. So we used an approximative function of the B-spline. There is a lot of work regarding the use of B-spline for double glazing alone. So in our case, we had double glazing with the shader. And we were like in the model, you have all the parameters, but you try to estimate the coefficient of this B-spline. And this is for like we had the same profile for all the series, time series, and because we fit all the time series for the model. And in blue here you have the time dependent direct transmittance to the theoretical one, the one that was derived from the BSDF, from the ray tracing technique. So at first, I say that characterizing an adaptive facade can help you in the early stage design. So for such a system, for the shaded device, what you want to know as a constructor or designer is to know the optimal orientation of your configuration of this type of shading. So we have done two experimental tests with two different orientations, toward the south, toward the southwest. And here I'm comparing the daily energy, accumulated energy for double glazing alone and with this shading, means with the transmittance that was derived from the ERC model. So you can see here that we had in the south we had less solar gain inside that was transmitted by the shading, which means that the optimal orientation for this shading is the south. So as a perspective, in my work, PhD work, actually, we compare it with the double glazing. But normally, as a designer, what you want to know is how performant is your system in like comparing to another system that is already in the market, that is conventional, like a Venetian plant. So one of the perspectives is to compare the performance of this non-conventional shading system with a shaded device or Venetian plants or ruler plants. So yeah, I will defend my PhD July, 8th of July. So there's going to be a link that will be available. And yeah, if you are around Bordeaux, a buffet that is Moroccan. And yeah, so thank you everyone for your attention.
Thank you very much. Any quick questions? Very good. Okay, Hans.